Hello to everyone, our dear participants and dear Dr. Bronstein. Thank you very much for joining us. And my name is Dmitry, and I'm a member of a team who organizes this conference at Mila. And I would like to take some time and introduce briefly our conference and our main goals. So AI Helps Ukraine is a student-led fundraising conference in AI, and our main goal is to bring together the leading experts in the field of AI and promote AI and raise funds for humanitarian help for Ukraine. And so far, we have had a number of amazing speakers. And today we're very happy to have Michael. And next and on December 15th we will have Volodymyr Kuleshov. On last Thursday we had an amazing in-person event, which was a big success. We had a number of great talks, a big number of participants, very good networking session with some Ukrainian food. So we're very grateful to those who joined and to all our speakers who joined, who contributed to online and in-person to talks. And it would not be possible without a very big organizing team of volunteers and speakers. And now I would like to talk more about why we are doing this, because actually, as you know, it has been months since the Russian invasion in Ukraine began, and the level of destruction and suffering inflicted on the civil population is beyond any understanding. And in Ukraine, nobody is left unaffected by this war, and there are, like, before the war, they were just normal people like us who were living their lives, bringing their kids to school, to home offices. But now the war came to their home, and every day they are living in uncertainty. They don't know what will happen. Will there will be new airstrikes or not? And within the 9 past months, around 13 million people have been forced to leave their homes, and estimated of 18 million people need humanitarian aid, and around 15 million people require some psychosocial support. As you can see in the photos, the destructions from the war are quite huge. In the photo on the top, it is a photo of an like leftovers from the air missile, which landed just on the kids' playground in the center of Kiev. And in the photo in the bottom, you can see typical results of presence of Russian troops in Ukraine. This is in the Kiev region. So also the critical civil infrastructure is a very common target of the Russian attacks, especially recently starting from the September. They intend to undermine our industrial production, spread fear, deprive civilians of heat, electricity, and water. And now the winter is approaching. Hundreds and thousands of people would be lacking food, heat, and electricity, and medical care. And for this reason, we got together because we understand we need to do something. And if everybody does something, it will eventually bring to some good outcomes. So we are reminding you for supporting our case through donations or just through simple things as retweets of our events, participation in our events, and sharing information. So the money that we are collecting will go to the support of the Ukrainian hospitals, which are in big need of such devices, which are called negative negative pressure therapy, wound therapy devices. So basically, right now there are a number of civilian people and who got injuries which are very deep, and in order to heal them, we need specialized devices which were not actually needed before the war, because there were no such wounds typically. So they are quite expensive, and this device basically they help heal the wounds. But every amount of the donation counts. For example, $20 you can buy a food basket with 24 items. So we encourage you. We don't have any particular sum that we're asking for. Any amount will count a lot and will help us. And even simple retweets, as I said earlier, will already be very helpful. So the biggest power is in unity, and our teams believes that that we can make a difference with every donation. So finally, last and not least, we would like to thank our partners, Mila AI Research Institute in Quebec, who kindly helps us with logistics and venue. The Ukraine Medical Support is a Canadian non-profit organization which helps us with the logistics of the donations and humanitarian aid. And actually, we're collaborating with them to get the information about what is needed most and what we need to, like, in order to spend our money with the best outcomes for Ukraine. Also, we would like to thank our first official corporate partner, Google, and also Ivado Labs. And with no further ado, I would like to give a word to Michael, who will introduce our today's speaker.
Yeah, thank you, Dmitro. I'm Michael. We'll be introducing another Michael. Yeah, we're very happy to have here today Michael Bronstein. Michael is the DeepMind Professor of Artificial Intelligence at the University of Oxford. Previously, Michael had an appointment at Imperial College London and Stanford, MIT, Harvard, and he is a recipient of many, many awards, including Royal Society Wilson Research Merit Award, ERC grants, Google Faculty Awards, Amazon AWS Awards. Michael is fellow of IEEE, BCS, Alice, ACM Distinguished Speaker, and Michael is a serial entrepreneur and supports many startups in the field of geometric deep learning. So generally, Michael is one of the godfathers of geometric deep learning, and it's pretty much a role model. A lot of researchers look up to, and yeah, I'm very happy that Michael had the time to join us today. And yeah, Michael, take it away. The floor is yours. We can start the talk.
Thank you very much. So let me see if I can now share my slides. I currently don't see it. Sorry, guys. Can you help me? Okay, yeah. Now I see it. Okay. Right. So thank you very much for the invitation, and it's a great pleasure to be here, especially given the important cause and which I totally and fully support. As you probably know, I was born in Russia, or in the Soviet Union, and well, since February 24th, it's for me personally, and probably for many family members, it's been a kind of a black hole. So yeah. So I would like to talk about what we've been working on, geometric deep learning, and this broad topic, and how it can be applied to different problems that could potentially in the future maybe even change the way that we cure diseases and save lives. For example, drug discovery and drug development. So geometric deep learning, before we understand what it is, if you don't know, let me start with a quote. So we'll take you a little bit back in history. And the first quote is from Hermann Weyl. was a mathematician and one of the big names in mathematical physics of the 20th century. So he wrote thus poetically about the concept of symmetry. As wide or as narrow as you may define its meaning is, according to him, was one idea by which humans throughout ages have tried to comprehend and create order, beauty, and perfection. So that was actually in his book that was titled Symmetry, published in 1952, I think a few years before his death, at his retirement from the Institute for Advanced Study at Princeton. And in a way, he summarized the revolution that this concept of symmetry has created in physics, to which he contributed quite significantly. Now, the concept itself is geometric, and the Greeks attributed to symmetry almost magical properties, and Plato, for example, believed that the world consists of symmetric objects that nowadays we call Platonic solids, which is actually quite not a far cry from our modern understanding of crystallography and how certain types of matter are formed. But really the first formal axiomatic foundations of geometry are probably go back to Euclid, his seminal work, The Elements, where he constructed what nowadays called the Euclidian geometry, or sometimes still studied at school as the geometry. And it was a list of axioms based on which you could prove some results, theorems, and basically you can develop geometry entirely from these first principles. Now, what happened is that this geometry existed for more than 2,000 years. There was a kind of a problem with what is called the fifth postulate about parallels, and many illustrious mathematicians for more than 1,000 years broke their teeth trying to prove it, starting with probably the earliest example was Omar Khayyam, who is nowadays mostly known as a poet, but he was actually a polymath, a Persian mathematician. And the picture changed quite radically in the 19th century, when the first successful attempts to construct non-Euclidean geometry were made, and an entire zoo of different geometries emerged as a result. Projective geometry, which again was known before, but it was in the beginning of the 19th century, then different other types of geometry. And basically with this zoo, it was not even clear what defines in geometry and how they are related to each other. So a solution was proposed by Felix Klein. He was only 23 years old when he was appointed as a professor at the University of Erlangen in Germany. And as it was customary then in Germany, and it is still customary now, he was asked to deliver an inaugural lecture that entered the history of mathematics as the Erlangen program, where he outlined his view on how to approach geometry in the future. And the idea was kind of second algebraization of geometry, the first one being that of Descartes, the method of coordinates. And the idea of Klein was to formalize geometry as a space plus some group of transformations. So essentially studying the properties of geometric objects by how they're affected by certain transformations. So for example, Euclidean geometry can be associated with rigid motions, and a lot of properties of objects remain unaffected by rigid motions, such as areas, parallelism of lines, distances, angles, and so on. And you can make this group bigger and the transformations more general. So for example, you can go to affine projections or to affine transformations or projections, and less properties are preserved. And he actually claimed that projective view is the most general one, at least of those known at that time. He was also able to generalize the non-Euclidean geometries that were known at that time. And the non-Euclidean geometry, I'm specifically talking about constant negative curvature spaces that nowadays we call hyperbolic geometry. So he initially thought was not very high opinion of these kind of constructions, so he called them the so-called Euclidean geometry, but then he apparently changed his mind. And then it took about 50 years to incorporate more general Riemannian geometry, mainly by the works of Elie Cartan in the 1920s. So the importance of this work was not only felt in mathematics, where it didn't have only impact on geometry, but it was more a cultural shift, and it created new fields of study such as algebraic topology or category theory. But also in physics, it became clear that you can derive all physics from considerations of symmetry, And this is the kind of symmetry groups that form our modern understanding of physics, what is called the standard model. So what we call external symmetries that give rise to the Minkowski geometry of the special relativity, what is called the Poincare group, and the internal symmetries that define different types of interactions. And this is describes how particles, different types of particles and different types of interactions work. And I can quote another physicist, this time this is Nobel laureate Philip Anderson, that very laconically said that it's only slightly overstating to say that physics is the study of symmetry. Now, it's all great, but how does it all relate to deep learning, which is probably why we are all here, right? It's a conference about AI, so it's so far is great about geometry and physics. Let's talk about deep learning. So one analogy that I see is that in deep learning, we also have this zoo of different type of neural network architectures that maybe historically have been developed for different types of applications or data. Like convolutional neural networks, for example, originally developed for images, or recurrent neural networks for sequences or for acoustic data. And graph neural networks originally actually developed in chemistry for graph structured data, for relational data, and so on and so forth. So apparently, there is no common denominator that unifies all these architectures, and therefore we need to study each of them separately, and then we don't really understand what are the common principles. So geometric deep learning is a kind of a program in the spirit of the Erlangen program that tries to bring all these methods into a common blueprint and try to derive them from first principles. And these principles are exactly the same that inspired Klein. These are principles of invariance and symmetry. So if we look at the problem of machine learning in a simple setting, right, if you consider supervised machine learning, it's essentially, you can say that it's glorified curve fitting. So let's say that I have an input of images of cats and dogs, and I want to classify them into these binary labels, right, or a cat or a dog. So basically what I need to do is I need to approximate a very high dimensional function that takes as inputs these images, right, that I can represent as points in high dimensional space. And a class of such functions that could represent such functions are neural networks that are known since the 50s. And it is also known since the 80s or the 90s that they're universal approximators, right? So I can take just 2 layers of a perceptron, and this allows me, at least in principle, to approximate any continuous function to any desired degree of accuracy. So there is a class of results that show this. Now, if I take my example of cats and dogs, then the thing that characterizes it is that the problem is high dimensional. So the inputs are not 2-dimensional vectors or not 3-dimensional vectors. So they are vectors in hundreds of thousands or even millions of dimensions. That's typically the number of pixels, right, or the size of the images that we operate with in modern times. And what happens is that everything that we know about approximating functions from approximation theory, from results in mathematics, actually do not apply in this situation. And you can take a class of regular functions such as Lipschitz continuous functions, about which we can tell everything in 2 dimensions or in 3 dimensions. We can have exact bounds on the errors that we incur. The moment that we start increasing the dimensions, these bounds will not scale well. Basically, they will become exponential with the dimension. And this is a phenomenon that we typically call the curse of dimensionality. Now, this is, of course, a problem because most of modern machine learning deals with high-dimensional data. And it is especially acute in problems such as computer vision, where even very small images are very high-dimensional. And here's an example. Let's say you want to classify these images, right? So this is MNIST digit 3. It's a 32 by 32 pixel image, which is about 1,000-dimensional vector. I can input it, of course, I can parse it into a column and input it into a multi-layer perceptron neural network. Now, if I just shifted the same image by 1 pixel, the input that is column stacked will change dramatically. And now I will need to show a lot of examples of shifted digit 3 in order to teach the neural network that it should be classified in the same way. So this is what we typically call data augmentation. Now, the new generation of neural networks that emerged in the 80s and in the 90s was actually inspired by research done in neuroscience on the structure and the function of the visual cortex of the brain. So initially it was the neocognitron architecture of Fukushima, and then of course the classical convolutional neural network by Jan LeCun and co-authors. And as we'll see, these networks, maybe without explicitly realizing it, implemented some of the principles of geometric deep learning, in particular in the local connectivity and sharing of the weights. Now, in many applications, we don't have signals that live on grid structured domains like what we have in images. So here's one example of a molecule, and if you're interested in specifically, that's a molecule of caffeine. And let's say that I want to predict some of its chemical or physical properties, for example, how strong it binds to certain receptor, or whether it's dissolvable in water, and so on and so forth. And this is crucial, for example, when we want to virtually screen or discover new drugs. But in this case, I don't even have an order in which I can collect the features of the nodes of this graph that represents this molecule and pass it into a neural network, because here any permutation of the nodes will be a valid ordering. So here I need to deal with significantly bigger space of ambiguities. And there are many examples of such data. Molecules are one example. Another example are social networks. So these are gigantic graphs representing how people interact with each other. In biology, we also have what is called interactomes, or interaction networks, where different entities, different biochemical entities relate or interact to each other, and so on and so forth. So we need some principled approach to be able to deal not only in retrospective to derive from first principles some of the classical architectures like CNNs or RNNs, but also to be able to develop new types of architectures that will be able to apply to new types of data. So if we go back to our example of cats and dogs, actually the problem that looked dimensionality cursed is not that hopeless, because in this example, we know that our input is not just a d-dimensional vector. It lives on some geometric domain, which in this case is a grid. So the structure of this domain and the symmetry that we can associate with it, which is the group of translations in this case, can actually help us reduce, cope with the problem of the curse of dimensionality. And specifically, what we'll be looking at is capturing the way that the symmetry group acts on the domain, and the way that it acts on images or signals that live on this domain through some group representation, and then incorporating the symmetry into the function, right? Our classifier that in our example of cats and dogs that will be applying to this data in a way that this classifier respects this symmetry in the form of invariance or equivariance, right? So we have these three components. So we have the domain with the symmetry that actually can be separate from the domain. It depends on the problem that we are dealing with. We have signals that live on the domain, and the symmetry group from the domain acts on these signals for group representation. And then we have functions that eat these signals, and they respect the symmetry group in some way. So one example in which the function can respect the symmetry group is in the form of invariance. So by invariance, I mean that no matter how the group acts on the input, the output remains the same. And a good example is object detection. If I want to say that this is a cat, no matter where the cat is located in the image, it's still a cat, right? So I want here a translation invariance. Now, if I want to segment the cat from the background, then the input and the output of this function has the same structure, and I want the input the output to be translated in the same way as the input, right? And here we are talking about a slightly more general notion that is called equivariance, right, or shift equivariance in this specific case. And this gives us a very general blueprint that allows us to build neural network architectures. So we'll typically have a sequence of equivariant layers, maybe interspersed with some pooling operations. And then if the output, if we want classification, for example, to classify an image, right, or a graph, then we'll do some global pooling that will be invariant with respect to our symmetry group. And this idea can be applied to different types of data or different types of domains, whether it's grids, whether it's homogeneous spaces where the group acts transitively, whether it's sets or graphs, or maybe more exotic objects such as manifolds, meshes, and simplicial complexes, and so on. And what you can show is that many popular architectures that you know from the literature, such as convolutional neural networks, LSTMs, deep sets, transformers, graph neural networks, and more exotic stuff such as mesh CNNs or group equivariant CNNs, they all can be derived from the same blueprint by choosing the right domain, the symmetry group, and invariant or equivariant functions with respect to it. So today I would like to focus mainly on graphs, given that I don't have sufficient time. So graphs are really a system, a mathematical way of abstracting systems of relations and interactions. And you can use graphs to represent objects at small scales, such as molecules, to very large scales, such as social networks, right? Or interactomes in biology, or more or less whatever you want. So we'll assume for simplicity that our graph is undirected. So we have pairs of nodes. Each node is equipped with d-dimensional feature vector that I denote by x. And we can represent this structure by a matrix, a feature matrix that I denote by x, which will be of size n by d. N is the number of nodes, d is the dimensionality of the feature vector. And the structure of the graph can be represented by the adjacency matrix of size n by n. So we have a 1 where there is an edge and 0 where there is an edge. And by doing so, I'm already cheating because I assumed some ordering of the nodes, which is not given typically in a graph, because a graph is just a set, right? With some other set that contains pairs of nodes. So any ordering of the nodes will give me a different type of feature matrix or adjacency matrix. Or I can say that I have some ambiguity that is represented by a permutation matrix, which is a representation of the permutation group that is essentially the symmetry that underlies this object, our inability to canonically order the nodes of the graph. Now, two types of problems that we're interested in dealing with when we deal with graphs, when we deal with GraphML problems, is graph level problems, such as predicting a physical or chemical property of a molecule, or node level problems, such as, for example, detecting spammers in a social network. So in the first case, we are interested in functions that no matter how I permute the input nodes, the output should be the same. So we are talking about permutation invariant functions, right, that satisfy this constraint. In the second case, when I want to output node-wise predictions, I'm interested in functions that the output changes in the same way as the input. So if I permuted the inputs, the outputs should be permuted in the same way. So we are talking about permutation equivariant in this case. And graph neural networks are a way of implementing such functions. Typically, they will consist of layers of permutation equivariant operations implemented by message passing. We'll talk about it in a second. And possibly following by graph-wise aggregation or prediction, if, for example, we want to predict graph-wise properties such as solubility of a molecule. And you can also see it as an instance of the geometric deep learning blueprint, where the domain is a graph, the symmetry group is permutation, and functions are permutation equivariant operations that are achieved by message passing. So what is message passing? I can take a node in the graph and look at its neighbors, right? So here's node I. The node I sees its neighbors, right? Nodes that are connected by edges to it, and that's it. So it doesn't see anything else. So it's a kind of soup of the features of these nodes. So unlike the nodes themselves, the features are not unique, right? You can see here that, for example, the blue feature appears twice. So technically speaking, this forms a multiset, and I can aggregate all these features together. And what I need to do is aggregate them in a way that is agnostic to their order, because I remind you, I don't have any order. I can order them any way I want, right? So this must be a permutation invariant function necessarily, right? I don't have other ways, unless the graph comes with some predefined order. And I apply this function to every node of the graph, right? So I can apply it in different positions. I will get node-wise outputs, and you can easily show that this function will be permutation equivariant, right? So the output of this shared function phi at every position in the graph will be permutation equivariant. Now, the way that this function phi is chosen and defined really determines the different types of architectures of graphical networks that are abundant in the literature. And here we can distinguish between three major classes, or what we call flavors. So the first flavor is convolutional graphical networks. That's probably the simplest one. And in this case, the way that the information from the neighbors propagates, it is aggregated, for example, as a weighted sum, where the weighting coefficients do not depend on the features. They depend only on the structure of the graph. So, for example, adjacency coefficients that are denoted here by Aij. And by psi here, I denote node-wise transformations. For example, can be just linear transformations. And sigma is a nonlinear activation, typically a relu. A more general flavor is attention-based. The typical representative in this category are graph attention networks, or GAT. In this case, we still aggregate using some weights, but the weights now not only depend on the structure of the graph, but also on the features of the endpoints of the edge. And the most general flavor is message passing. So here we just have a bivariate function that depends on the features on both ends of the edge, and you can interpret it as a message that is sent from node J to update node I. So it goes from the more simpler to more general. More general doesn't necessarily mean better, because it consumes more memory, it's more computationally heavy, and there are kind of folklore claims that are made about convolutional architectures. For example, that they tend to oversmooth, or they cannot deal with heterophilic graphs. So this is actually not true. So we have a recent paper where we show that under certain circumstances, even these very simple models can be extremely efficient. I will talk about it later if I have time. So what is also interesting formally, that message passing, when we choose the aggregation to be injective, is equivalent to a classical result from graph theory that is called the Weisfer-Lehmann graph isomorphism test. And it is interesting, actually. So it was devised by Andrei Lehmann and Boris Weisferner, two Soviet mathematicians, in 1968. Actually, they were inspired by problems in organic chemistry, in particular in chemoinformatics and large-scale molecule search. And if you read their paper, in the acknowledgement, they give credit to George Vladuc, was a Romanian chemist that worked in the same institute with them. They acknowledged him for posing the problem. So I remind you that in the 60s, very little was known about complexity of different graph algorithms. And they actually thought that they found a polynomial time for testing whether two graphs are isomorphic. It was disproved by a counterexample that was actually known before a year later. So it's also interesting that well, you see that there is this relation between chemistry and graph theory. Actually, the term graph itself was introduced in the chemical context. So that credit goes to Sylvester. In 1878, he was talking about chemical graphs, and the term that is used in graph theory actually is that old, even though graph theory itself in certain forms existed for many years before that. So what is the Weisfer-Lehmann test? Basically, it's an iterative color refinement procedure. It starts with a graph where every node is colored in the same way, so it's a featureless graph. And what it looks is it examines the neighborhood of every node in the graph. So in this graph, we have two types of neighborhoods, right? So we have a blue node with 2 blue neighbors, and we have a blue node with 3 blue neighbors, right? Now, if we apply to them an injective function, think of it as a kind of hashing, it will produce two different outputs. So these will be the new colors. That's why the color refinement. So now we change the colors of the original nodes into two new colors, right? Representing the structure of these neighborhoods. Let's call them green and yellow. And now we can repeat the procedure again in the new refined graph. So now we have 3 types of neighborhoods, right? So we have green with 1 green and 1 yellow neighbor. We have green with 2 yellow neighbors, and we have yellow with 2 green and 1 yellow neighbors, right? So these will become 3 distinct colors. Let's call them violet, orange, and gray. Now, if I repeat the procedure again, the colors will not change, at which point I can output the distribution, the histogram. And the algorithm is constructed in such a way that if I give you another graph and the distribution of colors will be different, then I can for sure say that they are not isomorphic, so they're structurally different. But if the colors are the same, we actually don't know. So it's necessary but insufficient condition. And in fact, you can find examples of non-isomorphic graphs that cannot be distinguished by WL procedure. And here's one example. So these very simple graphs cannot be distinguished by this procedure. So it's, if you are working in chemistry, it is astonishingly disappointing, because in chemistry you have a lot of structures like this one that will be indistinguishable by the WL procedure. But that's of course not the end of the story. So fortunately, there is an entire family of Weisfeld-Lehmann-like tests that can test that have progressively more that have progressively increasing expressive power. So if these kind of graphs are indistinguishable by the standard WL test, then there will be some increasingly more regular graphs that cannot be distinguished by 3WL test, and so on. And you can find a family of what is called CFI graphs that will necessarily fail any KWL test. So as I mentioned, the analogy to the Weisfeld-Lehmann hierarchy is nowadays used as a standard way of reasoning about the expressive power of graph-neural networks. So the works of Xu and Christopher Morris from 2019 that made this link between message passing and WL test, basically established that the standard graph-neural networks are equivalent to WL test. On the other hand, there were works, for example, by Hagai Maron on the higher order graph-neural networks, KGNNs, that are formally equivalent to KWL. Not all of them, of course, are practical computationally, so they have complexity that is power k in the size of the graph, so it's not very practical. It's good for proving theorems. So there are interesting methods that sit somewhere between these methods. So they have complexity that is more similar to the standard graph neural networks, but they're upper bounded by 3WL, so they're strictly more expressive than standard WL. And there are several such works. Here, of course, I would like to shamelessly advertise our own. So that was collaboration of my PhD student Fabrizio Frasca with Hagai. So we had a paper called Subgraph Union Network, and there was another paper that we presented at Europe's earlier last week. So another standard thing that you can do in the literature is what is called positional or structural encoding. So structural encoding is a kind of positional encoding that also respects the symmetry of the graph. So if we know a priori that the Weisfeld-Lehmann procedure cannot detect certain structures, such as triangles, like in the example I showed, you can help it by counting these structures and attaching them as node or edge features. So for example, I can count the number of triangles in which every node participates, or a number of 4 clicks in which it participates, and these will be some extra structural features. And with this, we show that you can actually be not less powerful than the standard WL. You can also think of it as kind of problem-specific inductive bias. So if, for example, in chemical applications, structures that are prominent are cycles, typical aromatic rings, for example, of size 5 or 6, right, in organic molecules. And we show that we can significantly improve the quality of predictions over standard graph neural networks that are unable to detect these structures. So here's an example of predicting the solubility on the zinc dataset. And here's a favorite molecule of caffeine that shows these 2 cycles of lengths 5 and 6. Now, talking about slightly more exotic architectures. So this would probably be a good summary of the landscape of different graph neural networks. So the standard approach to graph neural networks is you're given the graph, and the graph has 2 roles. So it's both part of the input as well as the computational device, right? And the idea is that you use your graph to propagate information on it, and by doing so, you're discovering some of its structure, right? And you can tell exactly how expressive you are by making an analogy to the Weisfeld-Lemon graph isomorphism test. Now, you can take it to the extreme and say, ignore completely the graph and consider every node as an element of a set, right? So there is no interaction whatsoever between the nodes. And this is how deep sets or point nets operate, right? So it's an extreme version of graph neural network where there is no interaction. On the other extreme, you can say that assume that every node in the graph can interact. So we have a complete or a fully connected graph. And this graph can actually be learnable, for example, through the attention mechanism. So this is how transformers operate, right? So you don't somehow trust the graph that you're given, or you don't know the graph that you're given. You build it yourself from your node features. Now, you can also be somewhere in the middle. You can say that I trust my graph, but I don't like it, because some graphs maybe are not very friendly for message passing. So allow me to rewire it, to change it. And then I do message passing on this new graph, right? Or maybe I can also do rewiring while I'm doing message passing. So it can also be done dynamically. So with these kind of architectures, with transformers in particular, it is also common that we want to, especially in NLP applications, to represent functions that are not necessarily permutation invariant. And this is afforded by providing what is called positional encoding, right? So some features that identify uniquely the nodes in the graph. So similar techniques have also been applied to more general graph neural networks, and the structural encoding is one possibility of doing it. So on the other hand, you can also say that I don't like my graph because its structure is somehow too poor. So I can lift the graph into some more interesting, richer objects, such as cellular complex, and then do more interesting message passing on these objects. I can also consider my graph as a collection of subgraphs. So I can perturb my graph by extracting nodes or edges, and then do message passing that respects also the overall symmetry of this multi-set of subgraphs. So it's a product symmetry that includes permutations of the nodes in the graph and permutations of the subgraphs in the multi-set. And that's exactly the kind of methods that I mentioned before, our collaboration with Hagai and a few other works that have been done concurrently. You can also account for the symmetry of the data. So especially if your graph is not just an abstract topological object, but it has geometric realization like a molecule that lives in three-dimensional space. So you can expect not only the symmetry of the graph, right, the permutation of the nodes, but also, for example, continuous symmetry that reflects or rotates or translates the nodes of the graph in space. So these are equivariant GNNs or equivariant transformers, and this is actually a big deal nowadays in molecular modeling. And this was used by DeepMind in AlphaFold 2 under the name of invariant point attention. And finally, if you assume more structure, then your graph, for example, can be viewed as a grid. And in this case, graph neural networks become convolutional neural networks. So in this case, you have canonical node ordering. So you can give up the permutation invariance in favor of more powerful, more expressive aggregation operations. So let me say a few words about these more exotic architectures. So the topological message passing, essentially our graph is a one-dimensional object, right? So we have nodes and we have edges. So nodes are a complex of 0 dimension, right? And edges are cells of 1 dimension. So standard message passing operates by sending information along edges from one node to another, right? Nodes that are connected by an edge. But if we can continue this hierarchy, and we can say that we have also 2-dimensional, maybe high-dimensional objects. For example, we can say that every cycle in our graph will become a 2-dimensional cell, like it's shown here, which makes a lot of sense in molecules, for example. Then we can do some more sophisticated message passing. So we can also operate across different levels. We can do it hierarchically. So for example, nodes that belong to the same cycle can communicate directly through this cell, right? So they can send information through the cell and it reaches immediately the other nodes that participate in it, rather than going from one node to another along the boundary of the cell. And we show that it is strictly more expressive than Weiss-Frey-Lemon, and in applications like chemistry, but also other applications, these methods achieve better results in practice. Now, I mentioned already that the problem of graph rewiring, and the reason is that some graphs might be unfriendly for message passing. And this is because if I, for example, like in this case, I need to send messages from one side of the graph to another side, and the sides are connected. These are two blobs or two clicks that are connected by this very narrow bridge, by a single edge. Then I need to squeeze a lot of information into messages that go through this bridge. It results in bottlenecks or over-squashing phenomena. So in this case, what is very common to do is to introduce new edges that will alleviate this phenomenon. And there are many heuristics and many arguments how to do it properly. So actually, at the LOG conference, there was an entire session how to do graph rewiring and many interesting ideas and mathematical models and mathematical approaches. So what it means in terms of theory is that we actually cannot make any more the equivalence to Weiss-Frey-Lemon hierarchy, because the Weiss-Frey-Lemon hierarchy assumes that you use exactly the same graph to propagate information. So in practice, I think de facto in most of the modern implementations of graphical networks, you never use exactly the same graph as given to you in the input to propagate information as a computational graph. So you often, for example, subsample your neighbors, right? Or you do explicitly graph rewiring. So bottom line is that it's not the same graph. Even the use of, for example, negative sampling, right? So when you train your models using stochastic gradient, break this link to the Weiss-Frey-Lemon hierarchy. So we need something else to analyze the practical expressive power and practical capabilities of graph neural networks. So what could be this new tool, in my opinion? I think it would be very instrumental and very pedagogical, and also very, you can get actually interesting results, is to look at analogies between learning on graphs and physical systems. So you derive graph neural networks from some physical metaphors. And here in particular, we're looking at a dynamic system. So every node in the graph is some particle in some space that is governed by a differential equation that is parametric. So theta is some set of parameters dependent on time. And if we discretize this system at certain intervals in time, then the discretization, right? You can think of it as iterative solver for the differential equation. So this corresponds to layers. And you can think of a graph as some form of coupling between these differential equations. So basically, the rows of the matrix that describes the positions of the particles at every point of time are coupled along the edges of the graph. In some situations, if you assume that the graph is a realization in some continuous space, you can also think of the graph as a discretization of this continuous space. And what is also interesting is that the traditional approach of deriving graph neural networks from this perspective is you start with an evolution equation, right? Like the diffusion equation, and you parameterize the evolution equation. So you take every iteration, right, or every layer, and you you add some free parameters to it, like in GCN. An alternative is to start with an energy, like you do in many physical systems, and you write your evolution equation as a gradient flow that goes in the negative direction of the gradient of the energy, and you parameterize the energy, and then you derive the evolution equation as the gradient flow. And in this case, what you gain is better interpretability, certain constraints that allow you to, for example, to talk about the behavior of the system, whether it will be, for example, low frequency dominated or high frequency dominated, whether your parameters will be shared across layers, or whether your parameters will be symmetric. And what we show, actually, this is a paper that was written by my postdoc Francesco Di Giovanni and an intern who is now a PhD student in Cambridge, James Rowbottom. We call it GRAPH, Gradient Flow Framework. So using this framework, we show that even very simple and very naive graph neural network architecture, such as GCN, graph convolutional network, can be extremely powerful if it's done properly. So specifically, what we show is that if the channel mixing matrix that is used in GCN has sufficiently large negative eigenvalues, then it can induce high frequency dominated dynamics. In other words, you can guarantee avoid oversmoothing. And we can show that this allows us to deal with heterophilic graphs. So you can, of course, consider other physical models, right, like wave type equations. So we did it in collaboration with Konstantin Rusch and Sien Mischer from ETH Zurich in a paper that was presented at ICML this year that we call Graphql. And there are possibly other models, for example, from quantum mechanics that can be adopted as well. So here's another picture. So that is also a paper from this category of physics-inspired GNN models, or we call it also neural PDs. So here you can see the core data set, which is a citation network. Every node here represents a paper. The colors represent features, some low-dimensional projection of the node features, and the positions of the circles represent some positional encoding of the nodes. And the goal here is to do node classification into 7 different categories. I think it's based on the fields in which the papers were published. And what we are evolving here is both the feature coordinates and the positional coordinates and rewiring the graph at the same time. So basically there is kind of co-evolution of the domain and the data that lives on the domain, which is a little bit disturbing picture for people coming from machine learning or signal processing background, that you're doing a filtering of data, but the ground is shaking under your feet, right? So the ground is changing together with your filtering. So this is something that is disturbing maybe to signal processing people, but not to differential geometries. In differential geometry, it's actually very common to apply evolution equations to your domain, right? To manifold in particular. And probably the most famous of these evolution equations are the Ricci flows. So Ricci flow, you can think of it as a kind of diffusion equation of the Riemannian metric, even though its properties are quite different from diffusion equations. And just by analogy, so in diffusion equation on the left-hand side, we have the temporal derivative, and so here we have temporal derivative of the Riemannian metric. On the right-hand side, in the diffusion equation, we have the Laplacian. So here we have the Ricci curvature tensor, which is also second-order quantity. What it does to a manifold, so you start with something that looks like a dumbbell, so it's positively curved on these spheres and negatively curved in the bottleneck. If you run it backward in time, then it becomes more sphere-like and then collapses into a point. So Ricci flows were introduced by Richard Hamilton, and the goal that he was introducing this tool in differential geometry was to prove the Poincare conjecture. So Poincare conjecture claims that you can characterize high-dimensional spheres by whether you can take in 2 dimensions, the analogy would be a closed curve and collapse it into a point. So Poincare claimed that this also works in high dimensions, for example, in 3 dimensions. And indeed, Perelman used this mechanism to prove about 15 years ago, actually a slightly more general result than the Poincare conjecture. So that was one of the big breakthroughs in science in 2006. And you can ask again how it relates to graphical networks. So in graphical networks, I mentioned already that we have this phenomenon of bottlenecks and oversquashing. And if the graph has a particular structure, like small world graph, where the volume grows exponentially fast, right? So the number of neighbors of the neighbors of the neighbors increases exponentially with the radius. Then we run into a phenomenon that if we need to bring many feature vectors from the neighbors of the neighbors, we need to squeeze them into a single vector that represents our node, right? So basically everybody sends messages to the right node here at the top, and it's drowned in information. So mathematically, we can think of it as a kind of insensitivity problem, and we can formalize it by looking at the Jacobian of the output of a multi-layer graphical network at node I, and how it depends on the input at node S. And we can relate this Jacobian to the structure of the graph. through some power of the normalized adjacency matrix. Now, the graph structure, right, and the bottleneck is hidden here, but it's not clear how exactly it comes through. And we intuitively also understand that something that looks like a grid is probably less problematic than something that looks like a tree, which is a pathological example, right, where this decay is exponential. So we need something more nuanced or more geometric type of analysis to do it properly. And that's exactly what the notion of curvature is useful for, right? So I remind you that in continuous Riemannian geometry, what we mean by curvature or Ricci curvature is the following thing. We take two nearby points that are denoted here by P and Q, and we shoot geodesics from them in parallel and at the same speed. And we look at what happens to these geodesics. So if these geodesics converge, then we are talking about something that locally looks like a sphere. If they remain parallel, then we have a flat object, and it's Euclidean. And if they diverge, then we are talking about negatively curved or hyperbolic space, right? So these are actually examples of non-Euclidean geometries that were constructed first that have constant positive or negative curvature, right? The geometry of Riemann and geometry of Lobachevsky or Boyer or Gauss. Now we can do the same thing on a graph by analogy. So we can take a pair of connected nodes, P and Q, and look at edges that emanate from them. And if they tend to form triangles, then we are looking at something that looks like a click. So we can say that this has a positive curvature. If they tend to form rectangles or rectangles of certain type, then we are talking about grid-like structures locally. And if they don't form anything and actually become more distant, then we are talking about trees. So we can take it into a single number that counts certain number of rectangles and triangles that we call the balance form and curvature. So it's a combinatorial object that defines for every edge of the graph whether it looks like a click or like a grid or like a tree. And it reproduces the behavior of the continuous Ricci curvature in the discrete setting. And the main result of the paper, so that was the paper we presented at ICLEAR earlier this year, is that it is negatively curved or strongly negatively curved edges in the graph that are to blame for over-squashing. So in particular, if the curvature of the graph is bounded by some curvature delta, then there will be a large number of nodes for which this Jacobian, right, that represents over-squashing will be small, right? So it means that over-squashing phenomenon is strong. So it's over-squashing caused by strongly negatively curved edges. And the final exotic type of architecture, and I see that I should probably conclude soon, is diffusion on cellular shapes. So if you think of a graph, it's purely topological object, right? So same way as on the manifold, I don't have any notion of how far a point is from me or at what angle it is from me. I can only tell whether this point is in my neighborhood or not, right? So I have a notion of neighborhood or an open set, right, or topology, but not of metric or distance or inner product, right? So I need some extra structures in order to be able to define these notions. Same way in the graph, I can only then tell whether another node is my neighbor or not, right? So it doesn't have any geometry. So on the manifold, the way to prescribe geometry is through the notion of affine connection, which tells us how vectors go from a tangent space at one point to a tangent space at a nearby point. So it allows to do parallel transport. Now you can define something similar on a graph if you attach vector spaces to nodes and edges in the graph, and then you prescribe linear transformations that transfer these vectors across these spaces. So this is called the cellular sheaf. And you can define a physical system that propagates information between these vector spaces, and we can describe the expressive power of such a diffusion process, right, or a graphical network that arises from this physical system by studying different classes of sheaves, right, by applying certain restrictions to these maps that operate on these vector spaces. And for example, we show that the standard way of dealing with graphs, right? So when the graph is homophilic and we have one-dimensional vector spaces with symmetric relations, they can deal only with homophilic graphs, right? They can classify, for example, two classes, but they already don't work when the graph is heterophilic, when my neighbors are different from me in terms of their labels. So we need necessarily to allow for non-symmetric relations that allow to tell that my neighbor is different from me. We can classify more classes if we go to higher dimensions, and we can also study some other restrictions, for example, orthogonal transformations and so on and so forth. So what is interesting about this approach is that it doesn't resort at all to the Weisfeld-Lehmann hierarchy. So it studies the limit case, the asymptotic behavior of a diffusion process, and draws conclusions about the expressive power, right, or the number of classes that such a process can solve from this perspective, rather than making analogy to graph isomorphism. Now, I think this is quite drastically different and in some senses better approach than using the Weisfeld-Lehmann, because, for example, it doesn't assume anything that the graph must remain the same. So it's just to a large extent how you discretize these differential equations. So nobody prohibits you changing the graph as long as you conserve certain properties, right? That might be important in this differential equation. So I wanted to, well, with Michael's permission, to use his meme that he started at some point. That I think the idea there was to say that the graph neural community was overwhelmed with some of these topological constructions that are maybe not very familiar with within the machine learning community, such as Ricci flows or Simplicia or cellular complex or cellular shapes. So as we show in the recent papers, that even simple methods such as graph convolutional networks, when they're considered from certain perspectives or physically inspired architectures, such as discretization of a gradient flow, they are still not a toy knife, but actually quite powerful tool that actually busts some myth or some folklore that exists around and that are not powerful enough and that cannot deal with heterophilic graphs and so on. So we show that all of this is not true. So we might still use the good old little toy knife, and it's still quite powerful. So I don't know how much time I have actually, because I think I ran out of my time. So maybe I will go to conclusions. So so in the conclusions, I wanted to show you applications in drug design. So allow me maybe a few more minutes to say, because I need to leave to the expectations of the title from Euclid to drug design. So I would like specifically to talk about designing new proteins. As you probably know, proteins are everywhere. So more or less anything of substance or of importance in our body is mediated by protein molecules. And proteins are kind of this long snake chain of amino acids that under electrostatic forces fold into these intricate patterns. Predicting this folding has been a holy grail of structural biology, but it's even more interesting actually how to design proteins with desired functions. Now, somehow we used to conflate these three things: sequence, right? We know that from sequence we can come up with structure, and structure endows the protein with its function. But unfortunately, you can find proteins with completely different structure and same function. For example, they all bind the same ligand. We can find proteins with very different sequences but similar structures, so probably as a result of convergent evolution. And you can also find that you have very similar sequences of amino acids, but there is one unhappy mutation that completely breaks the structure of the protein. So a good analogy would be this lock and key metaphor. So where same way as you have a single key that fits into the lock, that the knobs inside the lock will fit into it. So you have a protein surface that geometrically and chemically is structured such that it will fit only one particular molecular ligand. And this is how most drugs work, right? So very roughly speaking, of course, I'm probably simplifying and trivializing it. You have a protein surface. It has holes in it, or pockets. And inside this pocket, there will be one molecule that will fit, or maybe a class of molecules that will fit. And if you plug the molecule into this hole, you will disrupt or activate some chemical reaction, usually disrupt. So usually these are inhibitors. So here is an example. So this is adenosine receptor, and this is a caffeine or a xanthine molecule from the same chemical class of caffeine that binds to it. Actually couldn't find an example with caffeine, even though I looked hard for it. But this is, of course, not every type of therapeutic target that we might be interested in. Other targets are considered to be hard to drug or even undruggable by small molecules. And these are specifically protein-to-protein interactions. When you have two proteins that naturally interact, and you want somehow to prevent them from interacting. So one such classical example is the PD-L1 or PD-1 complex, program death ligand. And it occurs in cancer immunotherapy. So this protein shows the immune cells that I'm a healthy tissue. And as a result, the immune system doesn't attack its own cells. What happens that, unfortunately, this protein is expressed by some cancer cells, and basically they evade the normal functioning of the immune system. So the idea of immune therapy is to, by blocking one of these proteins, to give back control to the T cells, basically to destroy them by the standard function of the immune system. Now, geometric deep learning can be used to design new proteins that will act as biological drugs or drugs that are themselves based on proteins. So that was architecture that we called Massif, developed in collaboration with a group of Bruno Correa at EPFL. And we use it to design new proteins, what is called de novo design. So protein that has never been observed in nature, never existed in nature. So we don't have evolutionary history or amino acid sequence. And the way that it works, we look at the target, we identify seed candidates that will bind, that we predict that will bind to this target, and then we build a protein around this seed. And we have examples that were actually built and for which we got a crystallographic structure. So this is an example of binders for PD-L1, so the oncological target. And you can see two proteins that were built, and these plots show their binding activity. This is the crystallographic structure, so it shows that the structure that we predicted really coincides to what occurs in nature. And this is another example. So this is probably one of the most popular and most well-studied protein in the past couple of years. So that's, you can recognize that's the spike of the SARS-CoV-2 virus, which caused the COVID-19 disease and wreaked havoc globally for a couple of years. So here you can see a part of this spike protein and where it binds the ACE2 receptor. So that's where the virus enters into the host. So we designed proteins that will bind to this part of the protein, of the spike protein, and will prevent it from binding to ACE2. And here again you can see two such designs. What is more interesting, well, we also have the structure, so this time by cryo-EM rather than by crystallography. You can also see that it works, it binds different variants of the spike protein that occur in different mutations of the virus. And also we compare its efficiency in pseudovirus neutralization as opposed to the AstraZeneca antibody. So that was clinically approved drug that was used in clinical practice to cure people with COVID. So of course, the binding affinities are probably not as great as we get with the clinical drug, but still, I remind you that this is something that was done in very short time, only computationally, in completely data-driven way. So no evolution, no mice, no lab experiments. So it was all done. It was all done with machine learning. So let me maybe draw this to the conclusions. So I showed you this picture in the beginning. So and this is somehow to convey the idea that deep learning is often said to be some kind of new form of alchemy that lacks vigorous mathematical and scientific foundations. So I hope that at least there is a viewpoint from which you can see the mathematical underpinning of many of the deep learning techniques that are currently being used. And the unifying framework is what we call geometric deep learning. You can use it to derive different types of neural network architectures in different applications. And probably the best conclusion would be to conclude with another quote. This one is from Helvetius, who said that the knowledge of certain principles compensates for the lack of knowledge of certain facts. So I will stop here. Thank you very much for your attention, and we'll be happy to answer any questions.
Thank you, Michael. That was fascinating talk. Still the best geometric deep learning talk quality I've ever seen so far. And props for the meme, yeah. So that fourth part now makes it totally complete. So I will start with questions I've prepared so far. So yeah, the geometric deep learning blueprint generally achieved quite some remarkable success in drug discovery and protein design about which you spoke recently, just at the second half of the talk. I was wondering, it seems that we'll really operate with very complex concepts, something like the reducible representations, torsion angles, and like all those physics-inspired networks. And when it comes to modeling complex interactions, like several proteins, interactions of between proteins, did we reach the ceiling here? So do we have enough of math and physics apparatus to describe it and to computationally model that? I'm pointing here to Schrödinger equation, which we can analytically solve for hydrogen, but then for anything more complex, we have to resort to some computational methods.
Yeah, it's a good question. So take it with a grain of salt, because I'm not an expert. So I know about proteins and molecules from some collaborations, but this is definitely not exactly my cup of tea. So I think that's a kind of situation where at the level of concepts, we know everything, right? So you can take any molecule and you can describe exactly what it will do, right? The problem is that if you want to do it very accurately, it becomes computationally intractable, right? So you need to solve quantum mechanical systems, and basically you need supercomputers to do it, right? And this is what molecular dynamics people have been doing for ages now. When you start to model it geometrically, right? So you basically abstract out, you say, okay, I have atoms, let's consider them as points. There will be some interactions, we can describe them as graph, maybe with some geometric constraints. Then, of course, a legitimate question, is this the right level of abstraction or the right representation, right? So it can be as good as any other representation. So our claim, at least in some problems, was that when you deal, for example, with protein interaction, right, where the two proteins bind under certain assumptions, then you can actually abstract out completely all the fold and just look at them as a molecular surface. And this was the original concept behind Massive. We've seen that it works well in some situations. Maybe it doesn't work in other situations where you have extreme conformational changes of the molecule. But this is one example where the right choice of the abstraction level can make dramatic effect. So whether we can discover the right level of abstraction automatically from the data for a given set of problems, I'm optimistic. I don't know how, but maybe at some point.
All right. Thank you. The second one I had, I was looking recently the other day through CASP15 results. They were recently announced just a few days ago, and if we look at the results, most of the top approaches use already AlphaFold-esque or AlphaFold derived or just direct improvements of AlphaFold system back from 2 years. So how do you think, did we reach the ceiling? Do we still have something to continue to invent, or we have already all the necessary stuff, now we just need to scale it up and to put into production?
Well, so what do you mean to put in the production? So AlphaFold predicts the protein structure from multiple sequences, right? That have evolutionary relation that is accurate in certain situations, right? So some things do not work, for example. This is a very different problem from design, Now, of course, you can say, and there have been some works, right, that say that you can use the forward problem to solve the inverse problem, to design new proteins with desired properties. From my understanding and what we've been trying, and I'm not saying that negative results necessarily imply that it's impossible. I'm just saying that we have not seen it successful, and I know that others haven't seen it very successful, is building completely new proteins that have never been observed in nature. So the ability to generalize, to my understanding, with these kind of methods is problematic. So basically, completely de novo designing protein from scratch without any evolutionary history. There should be probably other methods, not necessarily based on AlphaFold.
Mm-hmm. And what do you think about geometric deep learning and GNNs in general? Did we invent everything we need there? So drawing parallels to see to vision community, well, it's been the ResNets and maybe visual transformers for a while, and now community is more about applications, how we do more accurate segmentation or self-driving cars or something else.
Well, these are obviously quite orthogonal pieces of research, right? So you work on methods, improving understanding. So I think the expressive power has been quite obsessively exploited in the past years, but nothing is known about generalization power of graph neural networks, right? Mm-hmm. Little is known about generalization of graph neural networks. Now, a lot of these analysis is done, for example, assuming graph neural networks that are not realistic, for example, that are very, very deep, right, or infinitely wide, or things of this kind. So basically, making this kind of analysis in realistic situations is also very interesting. I personally find a lot of interest in looking at continuous systems and deriving graph neural networks as discretizations. So this is both interesting theoretically because it allows you to make some conclusions about behavior, right, and as a result, expressive and generalization capabilities, as well as their implementation. Because when you think of your system as a differential equation, then suddenly you also have some architecture in mind. I'm talking about hardware architecture, right? So this is very often an overlooked problem, how you actually implement your graph neural network on a processor that is not necessarily a GPU. GPU is not necessarily the most friendly hardware architecture for graphs. It was designed for completely different kind of workloads, right? Where you have single instruction, multiple data, but the data is of the same type, right? So you usually have a stream of pixels, for example, right? Or audio samples. It's not really made for a situation when one node has a million neighbors and another node has 2 neighbors, right? So there are other architectures that are being developed by probably NVIDIA itself, but also companies like Graphql that try to make architectures specifically friendly for graphs. But I think we can also help by designing algorithms that if are not necessarily friendly, at least aware and take advantage of the underlying hardware. And here, the mindset of differential equations automatically comes with also with how to discretize these differential equations and how, for example, different nodes resides in different parts of the memory hierarchy, right? And how messages that you send from one part of memory to another part of memory also take different time to propagate, right? So you have different latencies and so on and so forth.
Thank you. We have a few more questions. So one is from Maxim Kораblov. It should appear on the screen. So it's about physics-inspired models when the computation graph is changing. So is there a heuristic about the dimension of the space diffusion happening? And should we add additional nodes to the computational graph?
So I'm not sure. Well, Max, you should probably express yourself more clearly. So I'm not sure that I understand your question. So if the question, so if I try to guess what he meant here, so the way that the graph is constructed, so you can construct it based assuming that your graph is realized in some continuous space, right? And then you, for example, connect nearest neighbors. So this has been done, some of the first works. So we had, for example, in dynamic graph CNNs, collaboration with Justin Solomon from MIT. So there, basically the same feature space was used to construct the graph. A few incarnations of these kind of architectures, where there was a separate space in which the graph was constructed that was separate from the feature space. So the graph rewiring, for example, by Ricci flow or by topology diffusion, usually the rewiring takes place as pre-processing. So you embed the graph in some space. In case of, for example, methods like Deagle, the personalized page ranking embedding, you rewire it and then you do message passing on this new graph.
Right. Thank you. And yeah, Maxim can also elaborate a bit in the chat if we meant exactly what we meant. Then the next question from Nicole Zhang. It's about the performance on spike protein neutralizer is amazing. What do you feel is needed for ML design molecule to match or even surpass drugs found using lab techniques?
So it's very far from being a useful drug, right? So what we show is that it can be used in principle. Now, there are many other technical problems that I'm actually not an expert, but when you, for example, when you start manufacturing drugs at scale, so you need this protein to be makeable, right? So it's not that it's not enough that you're able to produce it in picoliter quantities in the lab and test it. So when you want to manufacture it at scale in a pharma company, then suddenly some designs that might work well in the lab suddenly will not work. Another problem is, for example, certain proteins can be immunogenic, so they elicit immune response. You don't want a drug that is destroyed by your immune system. This is actually one of the big problems in biological drugs in general, and one of the reasons why antibodies are considered to be a kind of safer bet, even though antibodies as well can produce immune response. So there are many problems that of, let's say, second order academically, but first or zero order when it comes to the actual pharma industry. And again, I'm not an expert here. There are probably many others.
Great. Thanks for that. And our last question would be from Alexandra. So it's about connection of expressiveness and those recent continuous GNNs. So did I get it right that the recent studies with gradient flow show that even simple GNNs are not limited by the 1WL test?
No, I didn't say that. So what I said is that actually we didn't make any connection to WL test. So I guess as a subset of message passing, they should be at most expressive as WL. The claim I was making is that what is often claimed about GCNs is that because the adjacency matrix, right? So the way that the GCN typically looks like, you have your features, you multiply them from the left by something that looks like either the Laplacian or the adjacency of the graph. From the right, you multiply by channel mixing, right? So you operate node-wise, and then you propagate information between adjacent nodes. So because adjacency looks like a low-pass filter, then basically the claim is that it oversmoothes. So the channel mixing is really crucial. And what happens is that you have an interaction between the spectra of the channel mixing matrix and the Laplacian matrix or the adjacency matrix of the graph. And the interaction is non-trivial. So we show that in the right setting, when the channel mixing matrix has sufficiently large negative eigenvalues, basically physically what it produces is repulsive interactions along these edges. And this is what allows to deal with heterophilic graphs. So if you think of it as a kind of particle dynamics, then we have certain directions in which particles attract and certain directions in which particles repel. So the attraction is what corresponds to oversmoothing, right? Everything collapses into a single point. But if there are directions where there is no attraction, there is a repulsion, so it's a kind of sharpening, right? So it's the opposite of smoothing. So that's the high frequency nominated phenomenon. And you can trade off these two by correctly choosing the structure of this matrix. So there are a few more constraints. For example, we use symmetric weights, which is a little bit counterintuitive, but actually there are results that show that the use of symmetric weights, not only in graphical networks in general, doesn't limit the expressive power, in the sense that the network is still universal approximator. But also there, probably you can say that it makes the system more stable to perturbations.
Yeah, and I would point further once again that this is the graphic or graph neural network as a gradient flows. So yeah, that's a very recent work by Michael's lab. Yeah, that's it for us for the set of questions. So yeah, let's wrap up. So thank you very much, Michael. Once again, that was a great honor, big joy to have you here this conference series. Thanks for finding the time and delivering such a wonderful talk. Yes, we'll have the next talk this Thursday by Vladimir Kuleshov on uncertainty-aware machine learning for sustainable food supply chains, and that would be the concluding talk of this year's series. Yeah, so Michael, thank you once again for being here.
Thank you very much for the invitation. It was a pleasure.